All right, AP Kim. Here's the second question for the office hour this morning, which is May 6th. This is question number 2 from the test 2010. So go ahead and work through question number 2. Give yourself 18 minutes. And when you're finished, you can come back to this video for the answers. So this is a great thermochemistry question. It's a calorimetry problem. Hopefully you do have a calorimetry problem on the test this year because these are very similar to solve. Part A says determine the change in temperature of the solution that results from the dissolution of urea. So all you're asked to do is compare this value, 25, to whatever this value is here. And this is a 21.8. Subtract the two, and your change in temperature is final minus initial. So 21.8 minus 25 gives you negative 3.2. You have to have that negative there. That's your answer for part A. According to the data, is the dissolution of urea in water an endothermic process or exothermic? Endothermic because it absorbs energy from the surroundings. That's why the temperature of the water decreases, because water is giving energy to this dissolution process, and that causes its temperature to go down. So that's your justification for endothermic. C, assume your specific heat capacity calorimeter is negligible. We don't have to worry about it. And it gives you specific heat capacity of the solution of urea and water. It's 4.2. Part I asks you to calculate the heat of dissolution in joules. You should be thinking Q. Q equals C times M times delta T. Well, we got the change in temperature from our graph. The C value is given to us in the problem. The only thing we have to get is the mass. And just a reminder for calorimetry, if you want to know the mass of it, you need to go back to your problem, find your mass of water. But you also need to consider, is the mass of the reactant going to be included? And the answer is yes in this case, because the solid urea dissolves and becomes part of the solution. Another indicator for that, it gives you the specific heat capacity of the solution, not the water, the solution. So you're mixing those two together. So it's the total mass, combined mass of the water and the urea that gets dissolved. If you have a problem where you just have something being combusted underneath or in a bomb calorimeter, you wouldn't include both masses. So this will give you joules. That's your answer for I. Then take your number of joules, convert to kilojoules, divide by the number of moles of urea that you had in the problem. And that's how you do the second part there. So here's how your points get distributed. Negative 3.2, you get the correct temperature change there. Endothermic with the justification that the temperature cooled off for 1 point. Part C, if you do solve that for your Q for your solution, your combined masses are 97.08. Plug that into your Q equals MC delta T, and you get 1.3 times 10 to the third joules. And you get 1 point for the correct numerical result for that, and 1 point for your setup. That setup means that you're using this equation. And then I, your molar enthalpy of solution, you would convert your grams of urea into moles. You get 1 point for that if you got this answer. And then take your joules, convert it into kilojoules, and divide by your moles, and you get this for your answer. And it has to have the correct algebraic sign. It must be positive because it's endothermic. That's the only way you can get that last point. If we move on, part D, this problem would not be on the test this year because we don't have this equation as part of our test, but we did cover this unit, so hopefully you could answer that question. You just plug in your delta G value, your delta H value, and solve for your S with the given temperature. You'd get this. And just to keep track of your points, you give yourself a point if you use this equation, and give yourself a point if you got this answer. You have to have the correct units. The per Kelvin is the part that you might have missed. It doesn't have to be in joules, so you could leave it in kilojoules per mole Kelvin. E, the student repeats the experiment and gets a result that's 11% below. All this is asking you is, can you do a percent error calculation? So take the value that we had previously. They multiply by 0.11 to get 11% of it and subtract it. I would just multiply this value by 0.89 and get your answer. So if you got that answer, you get 1 point. F, the student performs third trial experiment, but this time adds urea that's cold. It's colder than your water. What effect, if any, would using cold water have on the experiment? Well, the cold water is going to absorb even more thermal energy from, the cold urea will absorb even more thermal energy from the water than it would in the first experiment, which means if we go back to our experiment here, this temperature change would be even larger, be even lower value, so we get like negative 3.5 or something. What would that do to our Q? Well, larger temperature change, bigger Q, bigger Q means bigger enthalpy change. And so that's your answer here. There would be an increase in the obtained value for delta H solution because the colder urea would have caused a larger negative temperature change, or it would have absorbed more energy. You get 1 point for that answer with the correct justification. And your total for this problem, if you want to compare, 4.26 out of 10. That's your average. If you're beating that, good job.